All right, everyone, we're going for round number 2. I'm talking about the JK flip-flop. I made a video on this last night, and then the very tail end of it crashed and burned. It wasn't pretty. So let's go ahead and kind of introduce another building block that we actually have for memory. Now, we started off with the SR latch. The SR latch, remember, we had an issue with that in which we had a forbidden state in which basically Q and Q bar, they did not work because they were both the same. We never want those two outputs to actually be the same. So we built on that and we developed the D latch. Now the D latch, all it had was an enable signal and then basically a data signal in which as long as D was high, then we were in a set state. And if D went low, we were in a reset state where Q would go to 0, Q bar would obviously be reversed. And we avoided ever having any issue with Q and Q bar being the same. Well, one of the other elements that we can work with and that we're going to introduce in this class is actually the JK flip-flop. Now the JK flip-flop is actually quite unique in the fact that it's the first element that we actually introduce that is definitely synchronized. And what I mean that is with a latch, latches generally just work on a high enable. The D latch actually, as long as that clock cycle is high, then it can change its output at any given point during that high cycle. Generally, when we say flip-flop, we're starting to introduce this concept of edge triggering for the clock cycle. So more of a synchronized way in which we can actually change the output. Now, what I mean by a clock going to high trigger is when we look at the edge right here, the leading edge of that clock pulse, we only actually change the output or have the ability to change the output when that clock pulses go high. And there is a variation on the D latch in which we can actually make it into a D flip-flop by allowing for it to be edge triggered. And the reason why we actually want to deal with edge triggering as opposed to just an enabled high cycle is specifically because a synchronized system will allow outputs to only change at very specific points instead of any given point during that high cycle itself. And so basically, as the clock cycle just periodically parses through, then basically all flip-flops have the ability to change at the exact same time. And that actually saves a lot for us in terms of how functions are actually processed within the system and literally synchronizes the entire set of outputs. So the JK flip-flop is quite interesting because it doesn't really look as simple as a D latch or even what we would have as the D flip-flop. Because not only do we have the clock cycle, but we also have two inputs here as well, J and K. And as long if J is high and K goes low, then the output of Q goes high, Q bar is low. And conversely, if J, conversely, not conversely, that sounds weird. If J is low and K is high, then Q goes low and Q bar is high. But one of the other things that's very unique about the JK flip-flop is not only are we using feedback to these two NAND gates here, we're actually taking Q and Q bar and feeding it back all the way at the very beginning. And so the JK flip-flop has a little bit more complexity in terms of its nature. But the thing that makes it so unique is we have basically a hold state in which if J and K are both 0, then we sure enough hold Q and Q bar or their prior states. We hold those states. When J is low and K is high, then we are in a reset state. And if J is high and K is low, we are in a set state. But what's really interesting, if J and K ever become both high, we do what we call toggling Q and Q bar. So if Q was high and Q bar was low, if we toggle them, then Q would go low and Q bar would actually go high. Now the biggest question that always comes of students when we look at basically the D latch and then the JK flip-flop, and I actually looked this up and did a bunch of reading on it yesterday evening. Generally, folks say, well, the D latch is actually very, very specific and simplistic in nature, because as long as D goes high, then the output goes high. And if we are synchronized, it seems like it performs basically those functions in a very, very simplistic manner. And there's questions all over the internet of which one's actually better served within digital architecture, because one of the elements we don't actually look at in this class is also the T flip-flop or T latch. And the question really just comes down to, it depends. It depends upon the architecture that we're working with, what we're utilizing to develop it, whether we want to use a programmable gate array in order to implement our logic functions, or if we want to use discrete logic like we do on our chips. So it really just depends. And the JK flip-flop, from everything I understand, came before the D flip-flop. And so there was something about the use of the JK flip-flop with its essential diversity in the way that we could actually control it. So there is not really a good answer for which one's better. It just depends. So let's actually take a look at the functionality of the JK flip-flop and see if we can verify basically some of these conditions. And we're going to start off with basically a set state. So let's have Q prior, and then we're going to see if we can derive Q next, in which we would actually get a set state. So let's take a look at this. So here we're going to start off with Q being low, Q bar being high, and clock obviously has to be edge triggered high. And so let's actually cause a set state. So here J would actually be 1, K would actually be 0. So if we look at the 0 here and we go through and feed these through, so Q would actually be low down here, Q bar would be 1 up for this NAND gate. Let's take 0, let's feed this back over here, and then for Q bar, that's actually going to be fed back to this input. So let's see if we can verify the set functionality. So in this case, guys, we actually have 0 that's being fed down. And so here we got 1, 0, 0. So obviously the output of this NAND gate is actually going to go high. And so if we have 0 and then 1 right here, that holds this guy to be a 1. But if we look 1, 1, 0, then that causes that output. Actually, there's a 1 right here. That causes 1, 1, and 1. So here we get basically an output of 0. And we know that if we NAND 0 and 1, that causes this output to change to a 1. So Q next actually became 1. And now we actually take that 1 and feed it back down with this output. So 1 and 1 NAND it together, sure enough actually causes this guy to turn to 0. And sure enough, we do have Q next is actually being 1 and 0. So in fact, actually we caused a set state to happen. But obviously we would need to feed that back up to this guy. So that turns into a 0. Let's make sure we're consistent with all the outputs now being fed back to the input. So now we have a 0 that's actually been fed back up to here. So 0. And then sure enough, that 1 is actually being parsed all the way back to that output. So sure enough, if we have 0, 1, and 1 all NANDed together, that actually turns this into a 1. But obviously 0 and 1 holds Q next to be consistent. So there is basically a high Q next. And if that stays high, then if we have 0 and 1 NANDed together, there's still a 1 right here. 1 and 1 NANDed holds that to be 0. So in fact, actually we do have a true set state in which we actually have basically Q prior was 0 and 1, and then we actually flip that into basically 1 and 0. Okay, so that set state actually works. Let's see if we can actually prove out the toggle in which basically we have Q prior and Q bar actually reverse. So let's see if that works. So as we can see here, guys, sometimes it does take a couple of iterations to make sure that the functionality of this guy actually works and actually fully sets itself in the proper manner. So when we have the conditions of J and K both being high, then we actually need to go through and see if we can actually get basically a toggle effect happen, which 1 and 0 are actually going to reverse to 0 and 1. So let's take a look here, see if this actually works. So here Q is 1, and so that actually gets the input in the front of basically being 1, 1, and 1. Then here we actually going to take 0, and we're going to utilize that up here as actually being our input of 0 for the top NAND gate. 0 is fed to here, and then also 1 is then fed down to here. Let's see if we can actually cause this effect to actually happen. So 1, 1, and 1 NANDed together gives us in fact actually a 0. So let's see what we get on this guy. 0, 1, and 1. It causes 1 and 1 to actually be NANDed together. So let's see if we actually can get these guys to actually flip. So 1 and 0, sure enough, the output here goes over into, sorry, that should have been, yeah, that should be a 0 right there. So 0 and 1, so that causes this guy to turn into a 1. So Q next actually turned to 1. So that actually goes up here, and sure enough, if there is a 1 that now has actually been fed back to the top NAND gate, 1 and 1 NANDed together, sure enough, causes both these guys to flip.